So our last topic to cover from 1.5 is the even and odd functions, and we covered these today in class. We had this idea of reflections, things that had reflectional symmetry, and things that had rotational symmetry. And that Desmos activity, rotational, I can't talk and type right at the same time. And that Desmos activity did a really good job of visually showing you what that meant. So I'll try my best to do that here. So I'm going to go ahead and use some trig functions since they should be fresh in our brains from Math 104. Reflectional symmetry, we said we have that in our graph of cosine. So here's cosine of x. And so when we talk about reflectional symmetry, the little graphic in Desmos actually showed us rotating this thing around the x-axis, right? So this is if we did a reflection across that y-axis, we would end up with the exact same graph. You could think of it also as if we divided this in half at the y-axis and we had this side of the graph all nice and, oops, freshly inked, then we would end up right back where we were. I want to get rid of that. So we make the other half of the curve. We have the language that the book uses for this. It calls these even functions. This is typically how we refer to them in calculus. I'm going to use fxn for function. And we had another way to talk about them as well. We said symmetric with respect to the y-axis. And we talked about how we can't have symmetry with respect to the x-axis for something that is a function, because then it wouldn't pass the vertical line test. And then we wrote down a bunch of different possible examples, right? We had x squared, our little parabola. We had the absolute value of x. What else do we have? Oh, well, I guess we could talk about if we had x to the fourth. Technically, any of our constant functions, right, would have reflectional symmetry. But yeah, the reason this gets that name even is because if you look at any of these power functions, you're going to see even powers result in reflectional symmetry. And so we get the last little definition here. What happens is, and one of the ways to check this algebraically is if you plug in a negative x. So let's just say we're dealing with some value x. So we can see our graph is over here. So there's f of x. If we come over and we look at negative x, what should be true if we have reflectional symmetry is that when I folded my page at the y-axis, the point ends up at the exact same spot, even if I'm at negative x, right? So these are going to have the exact same output. So f of negative x is the same thing as f of x, and that's one way we can check our work and see if something is an even function. In fact, we called those the even and odd identities when we learned them in trig. What else was I going to say? Anything? Oh, and then we also had a nice discussion today in class. I want to thank Joey for his great question. And that was about the idea that we can mess with anything vertically and we will not mess up our reflectional symmetry. If we make any horizontal changes, we might get in trouble here. A horizontal shift, a horizontal stretch will be okay, right? But a shift will ruin everything. So as long as we don't do a horizontal shift, we should be okay here, all right? It should still result in something that has reflectional symmetry. And then rotational symmetry was much more finicky. It did not like pretty much any of our things. I think we'd be okay with a lot of the stretches, but we're not going to get away with any shifts, whether we're talking about vertical or horizontal. And that is our rotational symmetry. So these are odd functions. So I'll go ahead and use sine as our example. All right, so rotational symmetry comes if we were going to rotate this graph 180 degrees, turn our page 180 degrees upside down, well, the graph will look exactly the same. If we were to turn our page upside down, nothing will change. You could also think of this as doing both reflections. If we reflect across the x and reflect across the y, we'll end up with 180 degrees of rotation. So that is what we want to see for rotational symmetry visually. Anything that has rotational symmetry we call an odd function, and we will say that it is symmetric with respect to the origin, which is why shifts are a problem. And then we could write down some of our common rotational symmetry parent functions. We just wrote down sine of x, tan of x also, just x itself, x cubed, the cube root of x. All of those will have rotational symmetry. Oh, and we did the reciprocal function as well in class today, which is x to the negative 1. So lots of different functions that have that rotational symmetry. And then our algebraic property here is if I plug in a negative, so let's figure out where my original x is. Say here's x, it's here. If I plug in negative x, I come out the same distance on the negative side, we should end up with the same function value but a negative version of it because it's gone that 180 degrees down into that other quadrant. So we get out negative f of x. So we're going to use those properties to actually find out if something is even or odd. I'll just grab all of these questions because they're all pretty straightforward.